Nice. Hello, everybody out there in YouTube land. Good times for all. Zachary Zabala here if you prefer. In this video, this is another Crocheters Corner, but I'm not going to be doing any crocheting in these right now. We're going to be talking about electricity and going over some of Walter Lewin's his lectures. We already went over one. That was the last one that I did. But we're going to be doing some new ones now. We're going to go to the next one, lecture number 2. Yeah, the stuff that well, we're going to start off. Walter Lewin is an amazing teacher. He actually, I'm just going to go ahead and play his introduction to his 802 series here. Let's see, 802. Oops. Let's see if that does it right there. But yeah, we're going to be going over all of Walter Lewin's his lectures that he's done. Okay. There we go. Walter Lewin, 802. But yeah, an amazing teacher. He taught at MIT, physics at MIT for many years. Just an amazing teacher, really. And he was kind of outed, you could say. They really threw him under the bus and said that he was diddling kids, which wasn't very cool. Hey, Flatlander, how we doing? But his lectures are just amazing. He's a great teacher, and in the Crocheters Corner we did earlier, we covered his very first lecture. In this one, we're going to cover
content is provided under a Creative Commons license. Your support.
Lecture 2. Hey, Mackenzie, shout out. How we doing, brother? But yeah, I think at the beginning each one I'm going to play this little 5-minute and 45-second video clip of Walter Lewin's. It's him explaining what he's going to be teaching us in this course. I'm not going to talk too much about things we've already been taught unless they are pertinent to the subject. So you really should start off at number 1 if you haven't seen the first one. This is the second one, so just go back 1 video. I'm not going to number them or anything like that. I don't want a lot of trolls and people like that or anything like that coming in. So I'm going to, I don't know, radar a little bit. But here we go. This is Walter Lewin, amazing teacher. His introduction to the 802 physics course, electricity and magnetism.
MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Well, 802 is, of course, largely about electricity and magnetism. And at the heart of electricity and magnetism are the famous 4 equations. We call them the Maxwell's equations. It's quite a difficult course for students. And I go out of my way to also introduce many phenomena that they see around them and make those phenomena connect with electricity and magnetism. For instance, lightning. I do an electrocardiogram in class. I discuss metal detectors. I discuss musical instruments, magnetic levitation. I talk about northern light, which is very relevant to electricity and magnetism. I spend almost the whole lecture on particle accelerators. I tell them why the sunsets are red and why the skies are blue. I talk about rainbows, about halos, about glories. I talk about color perception. And since I do Doppler effect, I also talk about Big Bang cosmology. And then during my very last lecture, I introduced them to my research, the research I did during my early days at MIT, when I was making X-ray observations from very high flying balloons, altitude of 140, 150,000 feet. So my goal is, wherever possible, to make them see through the equations, to make them see the beauty all around them, and by doing that, to make them love physics. Well, the 802 course is the second course in physics. It's mandatory. It's in what we call a general institute requirement. You either have to take this course or you have to take one which is a slightly higher level, 802. So it is the basis that students get during their first year. 801, the Newtonian mechanics, and then 802, the electricity and magnetism. And if they go in...
Matt, did you hear that? He said this is the basics. So this isn't like some over-the-top and super advanced courses or anything like that. This is a basic course that they teach at the Maryland Institute of Technology. So all the stuff that we get from here is what they teach in probably most physics classes. So when we hear a lot of people making arguments for things, it's like, I don't know, you'll see. But yeah, this is just the basics.
Into physics, of course, they get a lot more. But if they never go into physics, then this is all they will ever see about physics, which is quite a lot, actually. We evaluate the students through traditional exams. The lectures are given in the main lecture hall of MIT, and then the students meet in smaller groups with professors. We call those recitations, which is largely problem solving. There are many events in this course. Every lecture is an event. And the students who have taken me will tell you that indeed going to my lectures is an event. I'm not a very traditional lecturer. So therefore, I would really like to think that each lecture is an event. We do have a contest, which is very, very popular. We hand to the students a piece of wood, some copper wire, a few paper clips, and 2 magnets. And the goal is to make an electric motor. And they get course credit depending upon how fast their motor is going. And this is really a real happening. It's an incredible event. And some of the motors are extraordinary in their design. If you and I would try to build a motor, you'll be lucky if your motor rotates 400 revolutions per minute. But let me tell you, some students go to the 5,000 revolutions per minute mark. It's really quite amazing, and they spend so much time on that. It's a wonderful event. It's really a happening. Well, my message to all educators is, what counts is not what you cover, but what counts is what you uncover, and this is often forgotten.
Did you hear that? It's not what you cover, but it's what you uncover. I get chills every time I hear that. Just an amazing man, great teacher. He is still on YouTube today, putting out videos. He has talked about flat Earth, saying he will not speak about it. This man has been dragged under the bus by his own, the powers that be, the people he worked for. So I want to know is, what did he do? Did he say no finally? I'm not sure. But whatever happened, we know it, when you're in the club, that you can with murder. And it's not until you break some of their rules do they throw you under the bus. But he was discredited. He was disbarred from MIT. He lost all his accreditation. Yeah, they took everything from him. He was stripped of everything. And they don't do that to you unless you do something, you know, to them. They don't care if you hurt common people, blah, 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 this and that. But if you break their rules once you're in the club. But he adamantly says he will not speak about the flat earth. He just will not. He apologized here. He says it's okay if you don't want to be his friend. He forgives you, but he will not discuss it. Very, very smart man, a very good teacher. And yeah, if you haven't checked out any of his stuff, it's worth a listen for sure. Anything that he puts out, really. He speaks with such compassion. It's fun to watch.
So there is a general tendency, not everyone, but a general tendency to ram too much down the throats of the students and overlook that's very anti-productive, because it goes one ear in, as we say in Holland, and it goes the other ear out again. So what you cover is not what matters, but what you uncover is what matters. And if you can somehow do it so that there are parts of the course that they will remember for the rest of their lives, that's even more important. If a student has come to my lectures on rainbows and halos and glories, for the rest of their lives, rainbows will never be the same. And they will always think of me when they see a rainbow. And in fact, sometimes 20 or 30 years after a lecture, they send me still pictures. And they say, Professor Lewin, I saw a rainbow and I thought of you, and here's a picture. And the interesting thing is, they sometimes send me a picture which is not even a rainbow, which is a glory, but that doesn't matter. What it shows is that I have succeeded in making them love physics, and that's my goal. And that should be the goal of every educator, to make them love physics.
Well said. Okay, we had already covered 802 Lecture 1 earlier. So,
my lectures.
Did that say Lecture 2 already? No, it can't. Let's see. Let's go down here. Electric charges and forces we had already covered. That's in the very last Crocheters Corner. Coulomb's law, polarization. So we're going to cover 802, electric field lines, superposition, inductive charging, and induced dipoles. Really neat stuff. So let's just jump right into it. I've already started watching it, it looks like, so we're going to have to jump. Oh, no, it started over. Cool.
Today, I'm going to work with you on a new concept, and that is the concept of what we call electric field. We spent the whole lecture on electric fields. If I have
one more thing before we get started. Electricity controls everything. I should play the beginning of the very first lecture to oh, it's so beautifully said and well put the way he does it. I'm going to. We're just going to listen to the very beginning. It's the first couple minutes. Come on, jump back.
I'm Walter Lewin. My lectures will in general not be a repeat of your book, but they will be complementary to the book. The book will support my lectures, and the lectures will support the book. You will not see any tedious derivations in my lectures. For that we have the book. But I will stress the concepts, and I will make you see beyond the equations, beyond the concepts. I will show you, whether you like it or not, that physics is beautiful. And you may even start to like it. I suggest you do not slip up, not even one day. 802 is not easy. We have new concepts every week, and before you know, you may be too far behind. Electricity and magnetism is all around us. We have electric lights, electric clocks, we have microphones, calculators, television, VCRs, radio, computers. Light itself is an electromagnetic phenomenon, as radio waves are. The colors of the rainbow in the blue sky are there because of electricity, and I will teach you about that in this course. Cars, planes, trains can only run because of electricity. Horses need electricity because muscle contractions require electricity. Your nerve system is driven by electricity. Atoms, molecules, all chemical reactions exist because of electricity. You could not see without electricity. Your heart would not beat without electricity. And you could not even think without electricity, though I realize that even with electricity, some of you may have a problem with that. The modern picture of an atom.
Okay, that was pretty much his description there, just showing you that everything can test and measure, it's all controlled by electricity in one way or another. Everything. You seeing, you hearing, you moving, you know, pretty much everything that goes on. Light, radio waves, it's all controlled by electricity. It's all electric. Everything we're in.
Today, I'm going to work with you on a new concept, and that is the concept of what we call electric field. We spent the whole lecture on electric fields. If I have a charge, I just choose Q, capital Q and a plus at a particular location, and at another location I have another charge, little q. I think of that as my test charge. And there's a separation between the two. This R, the unit vector from capital Q to little q is this vector. And so now I know that the two charges, if they were positive,
see, this is the math stuff that he really gets into that gets boring.
Q is negative, they would attract each other. And let this force be F. And last time we introduced Coulomb's law. That force equals little q times capital Q times Coulomb's constant
over epsilon zero
in the direction of our roof. The two have the same sign in this direction. If they have opposite sign, it's in the other direction. And now I introduce the idea of electric field, for which we write the symbol capital E. And capital E at that location P, where I have my test charge little q, at that location P is simply the force that it...
Yeah, isn't it, Adam? The guy's got so many chalkboards, it's awesome. And there's some that he uses a lot of them too.
But it doesn't have the little q in it.
See, this is all the stuff that I really don't, this is all the goobity garble math stuff that, but there's little nuggets of gold in between this stuff. So you just got to watch it and really pay attention and wait and listen. It's hard.
Such that if this is a positive test charge, then we say the E field is away
from Q if Q is positive. If Q is negative, the force is in the other direction.
You have just about as many toolboxes as he has a chalkboard, so you're up there, man.
That the force is on a positive test charge. What you have gained now is that you have taken out the little q. In other words, the force here depends on little q. Electric field does not. So the electric field is a representation for what happens around the charge plus q. This could be a very complicated charge configuration, and electric field tells you something about that charge configuration. The unit for electric field, you can see, is newtons divided by Coulomb in SI units. And normally we won't even indicate the unit. We just leave that as it is. Now, we have graphical representations for the electric field. Electric field is a vector, so you expect arrows. And I have here an example of a chart.
This is the good stuff, so pay attention here. This is where he shows you
by
stuff.
By convention, the arrows are pointing away from the charge.
It's
the same
positive
direction that a positive test charge would experience the force. And you notice that very close to the charge, the arrows are larger than farther away. That sort of is trying to represent the inverse R-square relationship. Of course, it cannot be very quantitative. But the basic idea is, this is of course spherically symmetric, if this is a point charge. The basic idea is here you see the field vectors, and the direction of the arrow tells you in which direction the force would be if it is a positive test charge, and the length of the vector gives you an idea of the magnitude. And here I have another charge -1.
And as you can see, all the arrows are facing in. It's like a vacuum.
Micro Coulomb, just it's a relative representation. And you see now that the E field vectors are reversed in direction. They're pointing towards the minus charge by convention. And when you go further out, they are smaller. And you have to go all the way to infinity, of course, for the field to become 0, because the 1/r² field falls off, and you have to be infinitely far away for you to not experience, at least in principle, any effect from the charge. What do we do now when we have more than one charge? Well, if we have several charges, here we have Q1, and here we have Q2, and here we have Q3, and let's say here we have Q of I, we have I charges. And now we want to know what is the electric field at point P. So it's independent of the test charge that I put here. You can think.
Yeah, this is the stuff that it gets so boring when he starts talking about all this stuff. But like I said, there's little nuggets hidden in here that you just have to go sift through all. I've sifted through this about 5 times. 6, 7, I don't even know how many times I've watched all this stuff. But I know it goes on with a little bit more math for a little bit. Oh, let's see. There might be a little nugget in there, though. You never know.
Pointing towards the negative charge. And if this one were negative, then I would have here a contribution E3, and so on. And now we use the superposition principle, as we did last time with Coulomb's law, that the net electric field at point P, it's a vector, is E1, influence of charge Q1, plus the 3, and so on. And if you have I charges, it is the sum over all I charges of the individual E vectors. Is it obvious that the superposition principle works? No. Does it work? Yes. How do we know it works? Because it's consistent with all our experimental results. So we take the superposition principle for granted, and that is acceptable, but it's not obvious. If you tell me what the electric field at this point is, which is the vectorial sum of the individual E field vectors, then I can always tell you what the force will be if I bring a charge at that location. I take any charge that I always will carry in my pocket, I take...
Oh, I'd love to just try and jump ahead to a spot where I know is good, but like I said, there's cookies and little gold nuggets all throughout this stuff.
Then it will be in the same direction as E. If it is negative, it will be in the opposite direction as E. If Q is large, the force will be large. If Q is small, the force will be small. So once you know the E field, which could be the result of very complicated charge configurations, the real secret behind the concept of an E field is that you bring any charge at that location and you know what force acts at that point on that charge. If we try to be a little bit more quantitative, suppose I had here a charge +3. And here I had a charge -1. Here's -1. And I want to know what the field configuration is as a result of these two charges. So you can go to any particular point. You get an E vector which is going away from the +3. You get one that goes to -1, and you have to vectorially add the two. If you're very close to -1, it's very clear because of the inverse R² relationship that the -1 is probably going to win. Let's, in our mind, take a plus test charge now. And we put very close to -1, say we put it here. Even though +3 is trying to push it out, clearly -1 is most likely to win. And so there will probably be a force on my test charge in this direction. The net result of the effects of the two. Suppose I take the same positive test charge and I put it here, very far away, much farther away than this separation. What do you think now is the direction of the force on my plus charge?
This will
very far away.
Kind of make you think.
Excuse me? Why do you think it's to the left? Do you think -1 wins? So you really think the -1 is stronger than the +3 because the +3 would push it out and the -1 tries to lure it in, right? If the test charge is positive.
Sorry, Travis. I know, I'm sorry, man. I just had so much fun this morning and I've been thinking about it so much that I went ahead and started the second one. If you want to jump in, let me know. I'll send you a link. Oh, yeah.
Imagine you all the
that
way
was
to Mass
mine.
Avenue. You think that this distance matters? Who thinks the force is in this direction? Who thinks it's in this direction? Very good. You've helped them, really. The force is obviously in that direction because if you're very far away, the field will be the same as if you just had a +3 and a -1 somewhere here, which is +2. So if you're far away from a configuration like this, even if you're here, or if you're there, or if you're way there, clearly the field is like a +2 charge.
Okay. I don't know. See, this is the kind of stuff that's all the, I don't want to say theoretical, because they've tested it, but applying this in nature, it's hard to it's hard to think. But pretty much what he's saying is when you're near charges, it could be a positive and a negative doing something. When you're real close, say you're right next to the -1 there, the -1 will win. But the further away you get from that +3 -1 charge, it's going to be a +2 until you get so close to the -1 that the -1 would actually take over. the positive will take over and it will actually push that charge away. It won't try to absorb it. So we're going to listen to what he has to say. Hold on, Adam's asking me a question here. See, that's the thing. These are charges that they apply to like a, I forget even how they do it, but they'll put a charge there and then they'll have a test over here and just test a spot. And this is all the nonsense stuff that I don't really, but still try to, when you're thinking about our cosmology, it's good to know how electricity acts and works. You know what I'm saying?
Yeah, it seems like a lot of mathematical, verbal.
Yeah, that's what a lot of it is. But then he'll do experimentation and show you examples. Well, not experiment, but he'll show you demonstrations. And then you try to apply that on a grander scale about it. And it's, yeah.
And falls off as 1 over r squared. So therefore, if you're far away, the force is in this direction. And now look what is very interesting. Here, if you're close to the -1, the force is in this direction. Here, when you're very far away, maybe I should be all the way here, it's in that direction. So that means there must be somewhere here a point where the E field is 0. Because if the force is here in this direction, but ultimately turns over in that direction, there must be somewhere a point where E is 0, and that is part of your assignment. I want you to find that point for a particular charge configuration.
And you haven't really missed much, Travis. It's mostly just been math up to this point, talking about electric fields.
So let's now go to...
Oh, he did show a little chart about, it had a +3 and then a -1 charge. And the +3, it showed how it was stronger. It was larger than the -1. And the positive is blowing out like a hairdryer, while the negative sucks in like a vacuum, is how he was showing it.
Some graphical representations of a situation which is actually +3, -1. Try to improve on the light situation. And let's see how these electric vectors, how they show up in the vicinity of these two charges. So here you see the +3 and the -1, relative units. And let's take a look at this in some detail. First of all, the length of the arrows again indicates the strength. It gives you a feeling for the strength. It's not very quantitative, of course. And so let's first look at the +3, which is very powerful. You see that these arrows all go away from the +3, and when you're closer to the +3, they are stronger, which is a representation of the inverse R² field. If you're very close to the -1, the arrows are pointing in towards the -1, because the 1 over R², the -1 wins. And so you see they're clearly going into the direction of the -1. Well, if you're in between the plus and the minus on this line, always the E field will be pointing from the plus to the minus, because the plus is pushing out and the minus is sucking in, so the two support each other. But now if you go very far away from this charge configuration, anywhere, but very far away, much farther than the distance between the two charges, so somewhere here, or somewhere there, or somewhere there, or here, notice that always the arrows are pointing away. The reason is that +3 and -1 is as good as a +2 if you're very, very far away. But of course, when you're very close in, then the field configuration can be very, very complicated. But you see very clearly that these arrows are all pointing outwards. None of them come back to the -1. None of them point to the -1 direction. And that's because the +3 is more powerful. And then there is here this point, and only one point whereby the electric field is 0. If you put a positive test charge here, the minus will attract it, the plus will repel it, and therefore there comes a point where the two cancel each other exactly.
Yeah, it's definitely relative to where you are, Trav.
Of electric field representation, which is more organized. And we call these field lines. So you see again the plus.
Yeah, it all depends on your position. It's relative to your position, how close you are to the -1 and the +3. If you're in between them, it will always flow from the positive to the negative. But if you're beyond where the negative can actually suck it in and absorb it, it acts like a +2.
And you see there the minus
Atmos
1.
ether.
If I release right here, or I place here, a positive test charge, all I know is that the force will be tangential to the field lines. That is the meaning of these lines. So if
See, this is the part that I don't get, because he doesn't ever show how they know this stuff for a fact. Like it travels in this direction, and he doesn't show you. You'll see. But I don't know. It's a lot of it makes sense, but it's just mathematical. I don't see any. I don't know. I'd like to have all the equipment that they had when they were doing these tests, how they actually know what direction that electric charge was moving in. You know, it's frustrating.
If I'm here, the force will be in this direction. If I put a positive charge here, the force will be in this direction. And of course, if it's a negative charge, the force flips over. So the meaning of the field lines are that it always tells you in which direction a charge experiences a force. A positive charge always in the direction of the arrows, tangentially to the field lines, and a negative charge in the opposite direction. How many field lines are there in space? Well, of course, there are an infinite number. Just like these little arrows that we had before, we only sprinkled in a few. But of course, in every single point, there is an electric field. And so you can put in an infinite number of field lines, and that would make this representation, of course, useless.
In every single point, there is an electric field. That's one of those little those are the little gold nuggets that he just drops all the time. There is no place that exists that doesn't have an electric field.
So we always limit ourselves to a certain number. If you look very close to the -1, notice that all the field lines come in on the -1. We understand that, of course, because the field lines want to go to the -1. If you're very close to the plus, then they all go away from the plus. They're being repelled. You can sort of think as these field lines, if you want to imagine the configuration, that the plus charges blow out air, like a hair dryer, and that the minus suck in air, like a vacuum cleaner. And then you get a feeling for there is on the left side here this hair dryer which wants to blow out stuff, and then there is that little sucker that wants to suck something in, and it succeeds to some degree. It's not as powerful as the +3 though. Have we lost all information about field strength? We had earlier with these arrows, we had the length of the arrow, the magnitude of the field was represented. Yeah, you have lost that, but there is still some information on field strength. If the lines are closer together, if the density of the lines is high, the electric field is stronger than when the density becomes low. So if you look, for instance, here, look how many lines there are per few millimeters. And when you go further out, these lines spread out. That tells you the E field is going down. The strength of the E field is going down. It's the 1/r² field, of course. You want to make these drawings, what you could do to make them look good, you can make 3 times more field lines going out from the plus in this case, then return to the -1. So the field lines are very powerful, and we will often think in terms of electric fields, and the line configurations, and you will have several homework problems that deal with electric fields and with the electric field lines. If an electric field line is straight, so I have electric fields, get some red chalk. Say we have fields that are like this, straight E field lines, and I release a charge there, for instance, a positive charge, then the positive charge would experience a force exactly in the same direction as the field line, because the tangential now is in the direction of the field line. It would become accelerated in this direction and would always stay on the field line. I release it with 0 speed, start to accelerate, and it would stay on the field lines. In a similar way, if we think as the Earth as having a gravitational field, it's 801 that word, gravitational field. But in physics, we think of gravity also being a field. If I have here a piece of chalk, the field lines, the gravitational field lines, here in 26100, nicely parallel and straight. And if I release this piece of chalk at 0 speed, it will begin to move in the direction of the field lines, and it will stay on the field line. So now you can ask yourself the question, if I release a charge, will it always follow the field lines? And the answer is no. Only in this very special case. But suppose now that the field lines are curved. So here are field lines, as you have seen in those configurations. It's very common. If now I release a charge in here, say I have a point charge here, it will experience a force in this direction. So it will get an acceleration in this direction. So it will immediately abandon that field line. So if now you ask me what is the trajectory of that charge, well, it could become very complicated. I really don't know. Maybe it's going like this. By the time it reaches this point, what I do know that then the force will be tangential to this field line. It will be in this direction. And so as it marches out and picks up speed, locally it will experience forces representative of those fields.
See, I'm not sure how they know this stuff. This is the stuff that kind of baffles me. There are ways of showing like the electric field, and he'll show us that. But testing, like when you add a charge here or add a charge there or this or that, I haven't seen how they do that yet. I don't think he shows that.
Field lines.
I may be wrong.
The trajectory. So field lines are not trajectories, and not even when you release a charge with 0 speed. Only in case that the field lines are straight lines. Let's now look at a field configuration which Maxwell himself, the great maestro, in some of his publications, put there. There's a ratio 1:4. And whether it is +4, +1, or -4, -1 is not important, because that's just a matter of the direction of the arrows. But Maxwell didn't put arrows in. So I leave it up to you. If it's +4 and +1, you have to put arrows going outwards. And what you see now here is this air blower effect. Think of them as both being positive. So there's the +4 trying to blow air out like a hairdryer, and the +1 is trying to do its own thing. And so you get a field configuration, field lines, which are sort of, not perhaps easy, but you can sort of imagine why it has this peculiar shape. If you put a plus test charge in between the 1 and the 4, then the 4 will repel it, but the 1 will also repel it. So there's going to be a point somewhere, probably close to 1, whereby the two forces exactly cancel out. Therefore, E will be 0 there. In a similar way, between the moon and the Earth, there is a point not too far away from the moon where the gravitational attraction and the gravitational attraction from the moon exactly cancel each other out. That's not to this.
He still throws in all that kind of stuff, which Kind of has to, I think.
Similar from this situation. So when you have charges of the same polarity, you always find in between somewhere a point where the electric field is 0. Let's now go to a very special case whereby I make the two charges equal in magnitude but opposite in sign, and we have a name for that. We call that a dipole. Plus charge is here and the minus charge is there. Situation is extremely symmetric, as you would expect, because they have equal power. There's one air blower upstairs and one vacuum cleaner downstairs. If you're close to the plus charge, notice that all the field lines go away from the plus. And if you're close to the minus, notice that all the field lines come in on the minus. You expect that. If you are far away from this dipole, now you have a problem. Before we had a +3 and a -1. And when you're far away, the +3 wins. So it's like having a +2 charge. If you're far away, you always expect the electric field then to be pointing away from the equivalent charge of +2. But if you add up plus and minus and they have equal magnitude, let's say +1 and -1, you get 0. So neither one wins if you're far away. And notice carefully, if you're very far away, see arrows either pointing out nor pointing in. Nature cannot decide. There isn't one that is stronger than the other. That makes dipole fields very, very special. In the case of the +3 and the -1, if you're very far away, it's like having a +2 charge, and the E field, when you go further and further out, will fall off as 1/r². With a dipole, your intuition sort of tells you that it will probably fall off faster than 1/r². And that is part of a homework assignment that you have this week. In fact, I can already give you the answer. You have to prove it. If you're far away from an electric dipole, the electric field falls off as 1/r³. It goes faster than 1/r². There is not a single point in space where the electric field is 0.
Okay, did you hear that? There is not a single space or place in space where the electric field is 0. Nowhere. That's something you got to have in your head always. There's no place that the electric field is 0.
You can think about that, why that is the case. So these field configurations can be rather complicated and can be very interesting, and each one has its own applications. Are dipoles rare in physics? Not at all. In fact, they are extremely common. You cannot avoid them. Remember last time I told you, if you have a spherical atom or you have a spherical molecule and you bring that close to a charge, let's now think of it, you bring it in an electric field. It's another way of saying the same thing. So we have a nice spherical atom or a nice spherical molecule, and we bring it in an electric field. The electrons want to go upstream the electric field vectors. They go against the direction of the electric field. And the positive charge wants to go in the direction, wants to go downstream. And so what are you going to do? The electrons will spend a little bit more time on one side of the nucleus than they would in the absence of that electric field. And therefore, you are, through induction, turning that atom, turning that molecule in becoming a dipole. If you have a little bit more charge on this side, averaged over time, you have the same plus on that side. So you make dipoles, so you like it or not. And later in this course, we will learn more about the polarization of atoms and molecules creating dipoles when we talk about dielectrics. And you will see that it will have can have an enormous impact on the properties of the material. Could I make you a dipole here in class? Oh yeah, that's very easy. To make one of non-conductors is not so easy in class. To make one of conductors is very easy. And I'm going to do that with these two spheres that you have. Look at these two metal spheres. Conductors, free electrons, so it's very easy for them to move. And I'm going to bring this rubber rod, which I will rub and becomes, I think, negatively charged, if I remember correctly. And I will bring that, say, close to these two, which are touching each other. So here is this one metal sphere. Here's the other metal sphere. And here comes the rubber, negatively charged. Ah, what's going to happen? The electrons want to go away, so this becomes negatively charged, and therefore this remains a little bit positively charged. For every one electron that is excess here, when I start it's neutral, there will be a positive excess there because charge is conserved. You can't create charge out of nothing. And now what I do, while this rubber is still here, while that rubber rod is there, I separate them. So here they're in contact with each other first. They have to be in contact. Wow, we get some visitors.
Don't be late. That means you, pretty boy.
I'm impressed. Thank you.
Just college stuff.
So what I do now is, while this rubber rod is still in place, I take them apart. And when I take them apart, this negative charge is trapped and this positive charge is trapped. And so I have thereby created negative charge on this one, positive on this one, and it's equal in magnitude, so I have a dipole. What I want to demonstrate to you is that indeed I have positive charge here, negative here, that there is a difference in polarity between these two. And that's the way that I will do the experiment. I will not show you that the amount of charge is exactly the same on each, which of course it has to be. So let me give you some better light, or we have to get the view graph off, the overhead. You see there for the first time an electroscope. We discussed it last time. It is a piece of aluminum foil, very thin, with a metal rod next to it. And when I put charge on the rod, it will also go into the aluminum foil, and they will repel each other. And so the aluminum tinsel will go to the right. And the more charge there is on it, the farther it goes to the right. So let me first put these two together, make sure they are completely discharged. And now I'm going to bring...
That's what he did. When he put his hands on it, he discharged it. When he touched it and had the electricity flow to ground. So there should be an equal charge on there now, since they're very good at
these two into
having electricity move between them, the metal.
Which is produced by this rubber rod. I have to rub with the cat fur, and I believe it was negative. But if you never have to remember whether it's negative or positive, of course, that is not so important. What is in a name, after all? But it happens to be negative. Okay, so now we go here. I bring it here. I hope that no sparks will fly over the extraction. And now, notice what I do. While the rod is here, I separate them.
Wow.
So as I was holding it there, things were going on in there that you and I couldn't see. But the electrons, the rubber rod is negative. Electrons were shifting in this direction. And this is now positive, and that is now negative. If I take this one, and I touch it with the electroscope, you clearly see that there is charge on it.
Now wait a minute here. That doesn't make any sense to me. If one is positive and one is negative, why would they separate? Shouldn't they stay and be attracted to each other? That just doesn't make any sense to me at all.
I bring it here. I hope that no sparks will fly over because that ruins the demonstration. And now, notice what I do. While the rod is here, I separate it.
Oh, he separates it with his hand. Okay, I'm sorry.
So as I was holding it there, things were going on in there that you and I couldn't see. But the electrons, the rubber rod is negative. Electrons were shifting in this direction. And this is now positive, and that is now negative. If I take this one...
no voltmeter. This is just to show that it has a charge. He gets in the voltmeter and stuff like that later, after he teaches us what volts are.
You clearly see that there is charge on this. How can I show you now that there is charge of different polarity on the other one? Well, the way I will do that is I will approach this electroscope by bringing this sphere very close to it. And if this charge is different than the charge that is on it, the electroscope the reading will become smaller. And why is that? Why will the reading become smaller? Well,
it's taking some of the charge off.
Here is the situation of the electroscope now. And here is that ball that you see on top, upside down there. If this is all negative, that's why it is apart. If now I approach this here with an object which is positively charged, and I claim that this one now is positively charged because this one was negatively charged. The electrons love the positive charge, so the electrons want to come to the positive charge. So these electrons drift down again. And so if they come down, fewer will be here, and so you will see this.
Makes sense.
However, I put here a negative rod, then the electrons which are here want to go further away, they will stream up, and therefore the reading will become larger. So you can always, through induction, test what the polarity is of your charge. Let's hope that this one is still holding.
And we learned all about induction in lecture 1.
Its charge while I was talking. So I claim now that if this polarity is different, and if it's still there, when I approach the electroscope, come very close, that the reading should become a little smaller without even touching it. See whether that works. You see, it goes down. You see, it goes down. It goes down. So through induction, I have demonstrated that this has indeed a different polarity from this one. If I approach it with this one, it would go further out, unless it already is at a maximum. Let's try that. See, it goes further out. So not only have I demonstrated that I created the dipole, but you've also seen that by means of induction, that you can demonstrate that there's a difference in polarity between the two spheres. If I create a dipole, and I put that dipole in an electric field, the dipole will start to rotate.
This is pretty neat.
Let's first talk about it, why it rotates, and then I will try to demonstrate that by making a dipole. Big one, this big, right in front of you, almost as big as the one there. So let's have an electric field, like so. And I bring in this electric field a dipole, a biggie. Here, this is the one I'm going to use for this demonstration. Ping pong balls on either side, they are conducting, and they are connected with a rod which is not conducting. And so here is this dipole. This rod is not conducting, and this is a conducting, and this is a conductor. And let's suppose this is positive, and this is negative for now. And I'll show you how we get the charge on it. Well, the positive charge will experience a force in this direction, always in the direction of the electric field, and the negative charge will experience a force always upstream. And now there is a torque on this. And when there's a torque on this dipole, it will start to rotate clockwise. And of course, if it overshoots the field lines, when it is in this direction, the torque will reverse. Very easy to see. And so what you will see, it's going to oscillate, and if there is enough damping, it will come to a halt more or less in the direction of the field line. And this is something that I can demonstrate. First, I have to make a dipole of this kind. And the way I will do that is the following. This is a metal bar. And here is there's these two ping pong balls. The one on this side has a yellow marker, the one on that side has an orange marker. And I'm going to attach them holding them up against this metal bar. In other words, here is this dipole. It's not a dipole yet. Metal, metal, and here is a metal bar. This is a conductor which connects them. I'm going to turn on the Van de Graaff here, and the Van de Graaff creates an electric field. So we have the Van de Graaff here, and let's suppose that this Van de Graaff creates positive charge. Sometimes the Van de Graaff creates positive charge on the dome, others can be designed to create negative charge on the dome. And remember, for now I assume that's positive. What will happen now? Electrons want to go in this direction. So this becomes negative. Protons, positive charge stays behind. So that becomes, through induction, a dipole. Because I have them connected. I have them connected with this metal bar. So these electrons can flow through this bar and end up here. Now, I remove the bar. And so when I remove the bar, I have created now a dipole. I have here
you like that?
an insulating thread, and I have a fishing rod. And at the end of my fishing
he wears
rod,
all kinds of
I
stuff
have
like
now
that
a
on his
permanent
shirts.
dipole.
I think the banana's next.
With that permanent dipole, I'm now going to probe the electric field around this Van de Graaff. I could have chosen the same Van de Graaff, but there's a reason why I picked this one. And as I walk around this Van de Graaff, you will see that this fishing rod, at the end is this dipole, that the dipole always wants to go radially inwards or outwards, depending on how you look at it, of this field. So I can probe this field and make you see for the first time that there is indeed somewhere here a strong radial field going in or out of the Van de Graaff. And now comes something very interesting, which I found out this morning for the first time when I did this experiment. Van de Graaff there is also positive when I run it. How do you think this dipole is going to align then if I walk into it? Will the negative ball be closer to the Van de Graaff, or will the positive? Doesn't happen, that doesn't mean that physics doesn't work. It means the two Van de Graaffs have different polarities. And we'll see what happens. So let me first then create a dipole. So here is the dipole. It's sorted out now. I turn on this Van de Graaff. So induction takes place. Remember that the yellow is pointing towards the Van de Graaff, and that the orange is away from the Van de Graaff. Okay? So I induce a dipole. Oh, I really should redo that. I don't know what happens when it... I have to remove the field first. Okay. The yellow was inside, right? Was that the way it was? Okay. Yellow inside. There we go. So now it's creating a dipole through this metal bar. And I break contact. And this should now be a dipole.
No, Adam, it's not just a steel bar. The dipole in his hand, it's two steel bars connected by a non-conductor. Is how he did it.
Field of the... So if the polarity is the same, yellow will go in.
Oh, you hear that thing cracking? I want a Van de Graaff that big.
I will try to swing it a little. Notice two things. It's going to line up beautifully radially, but the yellow is not in. The yellow is out. So the two Van de Graaffs have different polarities. But you will see they rotate nicely. And they end up beautifully radial. And when I go all the way around here, again, they may swing a little, they may oscillate a little, but through damping they will come to a halt. And look, the field is indeed beautifully radial, and the yellow is pointing outwards. The two Van de Graaffs have different polarities. So
now he had to know that. He had to. Like he said, a Van de Graaff is designed to either be positive or negative. It's not like a Van de Graaff can be positive or negative. The same Van de Graaff. It's not like you turn it on one time, it's positive, and then you turn it off and turn it back on again, and it's negative. The way they're designed will do that. So he obviously knew that.
you've seen how we can create a dipole, and you've also seen how we often can make statements about the specific polarity. I can probe an electric field using grass seeds in oil.
This one's pretty neat. I'd like to try this one. I haven't done this one yet.
Grass seeds are elongated, and when I put a grass seed in an electric field, it will become polarized. There's nothing you can do about it. Here's a grass seed, and the electric field is like so. And so the electrons want to go as far away in this direction as they can to induction. And so this side remains positive. And so what is this grass seed going to do? It's going to rotate. It's going to line up with the electric field. And this is the way that I'm going to show you now field configurations in the vicinity of a dipole. And I will also show you then field configurations in the vicinity of two charges which have equal polarity. You may have seen this in high school with magnetic fields, with iron files. That's kid stuff. That's the easiest thing to do. This is the real thing. This is the electric field. I bet you've never seen electric fields which are traced by these mysterious...
Now, very important, there is a difference between the electromagnetic and the electric field. Two totally different things. He kind of went over that here, but he'll go over it more in a few lectures away. But yeah, right now he's just talking about the electric field.
Serious seeds. So I'll give you some light that may optimize the demonstration.
Yeah, this is a cool little test here.
First have to be oriented in a way so that it is chaos. The first thing you see is I'm going to make this, I believe it's going to be a dipole first, almost certain. So I'm going to charge one positive and charge the other negative, and then we'll see how these grass seeds will form each other. Watch closely. There you go.
Wow.
My goodness. That is a wonderful dipole field. Of course, we don't know which one is plus or minus because the grass seeds have no arrows on them. But you clearly see these incredible lines radially inwards or outwards on each one of the charges. And then you see these nice arcs in between. Who could see it easily? Okay, you got something worse for your tuition. Put a little bit more charge on maybe. Very clear. And now, which is perhaps more interesting, I'd like to show you the field surrounding two charges, but now the charges are both the same polarity. So we have to see
how that one was nice and symmetrical, and they were all lined up in Those were opposite charges. Now he's going to do...
Okay, now we'll try to make them both the same polarity. And then watch this hair blower effect that I told you about. Ah, look at that.
Now they're both
Great.
blowing away from each other.
Now you really clearly see these field lines, and you see in between how the two air blowers are competing with each other. Very impressive. All right, so that's the way you see field lines now, electric field lines. And some of you may have seen with iron files, magnetic field lines. If I have the Van de Graaff, and I have the Van de Graaff here,
What's going on,
let's
Dan?
suppose the Van de Graaff is positive. I don't know whether it's positive or negative. Let's suppose it's going to use the one over there. And I'm going to stand here on the ground, Walter Lewin. What is going to happen with me? Through induction, the electrons being sucked out of the Earth and coming up because they want to go close to the positive charge. So I will become negatively charged. What will the field lines do? Oh, they will be extremely complicated. Very complicated. But something like this maybe.
Now notice that when he's drawing these, he'll explain this later, but I just want to bring it up now. Everything will come off of that object at a 90-degree angle. It always starts perfectly straight. He might even mention it right now. But this is so important when we're talking about water and everything else, and how it is stuck to the earth. It's going to follow the electric field. It will be 90 degrees parallel to the electric field, water. So if the electric field is not perfectly level, then water will not be perfectly level. Everything follows the electric field lines.
Something like this. Some may come out here. Some may end up on my neck here. Some may go here, like so. Very complicated field configurations. But I want to probe that field somehow, a little, get a feeling for what that field is like. And the way I'm going to do that is I'm going to put a charged balloon. There you see the balloon, it's a conductor. I'm going to put a charged balloon and put it here, say. Well, if it is a positively charged balloon, it will take off in that direction, right? The force is always tangential to the field lines. It will abandon the field lines. It won't stay on the field lines. There's a lot of damping on the balloon. That's why I chose a balloon. So it will move relatively slowly, and it will ultimately maybe add up on my head right here. Once it adds up on my head there, so it comes in maybe like this, now it will get the negative charge from my head, and so it will become immediately negatively charged, and so the force now will reverse and will be in this direction, tangential to this field line. And so it will go back. When it hits the Van de Graaff again, it will get positive charge, reverses polarity, and it will go back. And so it will bounce back and forth between me and the Van de Graaff, and that gives you some rough feeling of what this field configuration is about, although I want to remind you that the charge does not follow exactly field lines. So I'm going to sit here, and I will be part of this. That's probably going to be positive. I will automatically become negative. There's nothing I have to do. All I turn is the Van de Graaff, and we have to put a little bit of charge on that.
Now, he's kind of cheating, folks. He is holding the discharge wand in his hand, which is negatively charged. Or it's the opposite charge of the main sphere of the Van de Graaff. So by him holding that, he is automatically charging himself up with the opposite particles. Now, if he was holding something positive, it would go straight into the ground. But I'm pretty sure this must, I don't know what, oh, this is a totally different Van de Graaff than the one he was using earlier. This is probably a positive one then. But here he goes.
That balloon. It will probably do that by itself, but I can always give it a little kick so that it goes to the Van de Graaff. There it goes. Oh,
I've done this one myself. It works just like this.
Because my glasses are a good insulator, so I better take my glasses off. so that every time it hits me, changes polarity.
It's one of the things that makes him such a great teacher.
So this is the way you can do physics and have fun at the same time. See you Monday.
And that's the end of lecture 2, folks. Yeah, just amazing stuff. This one didn't really get too much into like how things work here on Earth so much. This was more electricity acting within a field, close to each other, things like that. This lecture wasn't as fun as the last one for sure, but you still learned a few things. Like I said, Walter Lewin, he's just an amazing teacher. And he's still here on YouTube, putting stuff out. He was blackballed out of MIT. They threw him under the bus. So he obviously did something wrong against the status quo, so to say. But he's a very honest speaking person. He tells you that he is being deceitful sometimes. You'll see that in some of the later lectures. He's really trying to scream out, I think, that what he is teaching isn't 100%, but for the most part, it is. But not the next lecture, lecture 3, is one that is so important to how electricity acts on Earth. We're going to get into Gauss's law. I can't wait. Not going to start it now, though. It's already getting kind of late. But yeah, Gauss's law. Just great stuff. Try, if you want, go ahead and watch it, and then we can go over it together. Probably next Sunday. I might do 2 of these every Sunday. We'll see. I don't know. One early in the morning after, or blah, blah, blah. We're going to be moving those chats. Yeah, so one early Sunday morning and then one after Globebusters, maybe. You don't like the laws, but you'll listen. Yeah, but no, Walter Lewin, amazing teacher. And I've learned a whole lot from him. Done a whole lot of stuff. Reenacted a lot of his observations that he does here in his tests. And I can say that a lot of it is how he says it is. Because I went and did it myself. I wanted, I want to know. And Abe McKenzie and I are going to start messing around with some stuff. We're thinking about messing around with a vacuum chamber maybe, or something like that. But I don't know. We're going to get some stuff going. It's going to be pretty cool. But I guess I'll get going here, folks. Flatlander, thanks for joining me, man. I appreciate it. I hope, like I said, this one wasn't so much about, it's hard to apply this stuff to our cosmology. But I promise you, the next lecture, next Sunday morning, if I can wait that long, then this one's really going to blow your mind about how electricity works on a flat plane, on a sphere. They get into all that kind of stuff and all the laws that are based on the observations you can make yourself. Really neat stuff. But yeah. I know I probably should have waited. There's so many people live right now and all that stuff, and it's late over in England where a lot of my my watchers are from. But I had I'm probably going to watch number 3 here on my own. Yeah, Walter Lewin is a great teacher. And I just wanted to share this stuff with you guys. It'll be under Crocheters Corner. I'm just going to turn Crocheters Corner into these until we're done with them. Then I might go back to crocheting. I don't know. We'll see. But again, thanks for being here and watching this. Yeah, this is a physics education by an MIT professor for free. You really can't beat it. $27,000 a year worth of information that people pay. And they give it to you for free here. So enjoy it. So yeah, we'll meet back again. I'll try to put out a warning next time. I just kind of spur of the moment said, yeah, I'm gonna go live. So I went live. But next Sunday morning, I'm gonna do my best to wait till then. So hopefully I'll see you then. Yeah, I'm gonna get out of here. Good times for all signing out. As always, thanks for watching.